All right, let's move on to our next speaker. That's Ron Macnaughton. He'll speak to us about a web of new technologies and discoveries. Take it away, Ron.
Thank you. I've heard Michael talk on many occasions and showing amazing photos, and this might be the only time that somebody shows better photos than he has, for which I claim no credit. Every decade, a group of astronomers get together and they look at the long-term needs for astronomy and what investments they're going to try and wheedle out of governments. And the Webb was one of the recommendations, and it's taken 22 years before it actually has got into the sky, and it almost didn't make it, but I think everybody is quite happy it didn't get canceled. We all have a general idea of what the Webb is. Light comes from, infrared light comes from objects. It bounces off the gold mirrors. It bounces off another mirror, and then something happens to it. I'm going to be explaining. Primary mirror segments sort of go up to chest height of people, and the convex secondary is what's way up there, all covered with gold. And the reason is that gold reflects at infrared wavelengths particularly well, but given that it's soft, they cover it with some silicon dioxide. This is the part that I wondered how it worked and what it was. And I'm going to explain it, but I so wish I went to a place where Webb was to get a picture of me reflected on those mirrors. That must be an incredible thrill. Okay, here's the diagram. The light from the convex secondary mirror is not going straight back. It's actually off axis a little bit. And it goes through to a primary or a tertiary mirror, and then it reflects back, and then it goes in, and I'll explain more detail. So here it's come off axis, reflects off this mirror, which has a weird figure because it undoes all the normal problems with coma, etc., that reflectors are prone to. And then it reflects off a fine steering mirror that is continually adjusting things, and it goes into the focal surface. The tertiary mirror, as I said, has a really weird configuration because it's got to undo all the optical problems, and the fine steering mirror is continually moving. They talked about innovations and in terms of eye surgery, and I emailed Ralph, and he came up with beautiful comments as usual, that it's revolutioned ability to examine eyes with some equipment, probably not what's in the average eye lab, but they can see individual photoreceptors, and it makes laser vision correction more accurate. And I know a few people that had laser vision surgery and had struggles with it, so that's great news. We provided the fine guidance sensor, and this checks the apparent location of guide stars 16 times a second. Then it tweaks the fine steering mirror to keep objects within 6 milliarc seconds. So the accuracy of this is incredible. It also can track solar system objects that move compared to the deep stars, but it's a little less accurate, but it's still quite good. Although I'm only showing the 5 images that they released around July 12th, and they've also done some with planets, but that's not part of this. I'm going to take a little bit of a side trip into the electromagnetic spectrum and the atmosphere. We go from gamma rays to radio waves and beyond, and they all travel at the same speed, same phenomena. The only difference is wavelength, or conversely frequency. Gamma rays can have up to the energy of a ping pong ball that's moving. X-rays and ultraviolet injure us, and that's why our atmosphere is wonderful, except I have a bit of a sunburn in my neck now. Astronauts going to Mars, etc., are going to be exposed to it. I'll get to the visible stretch in a little bit, and then we have infrared below that, and then microwaves, and then radio waves, and the boundaries are all arbitrary. Visible is special for 4 reasons. It happens to be the wavelength of light that the sun emits most of. Second, the atmosphere is reasonably transparent to visible when it's not cloudy, which it too often is. And probably for that reason, our eyes have evolved the ability to see at that wavelength. I think other animals can do, others and not. The fourth thing I'm going to explain in a little bit. But above that is the microwave, and that's the region of wavelengths that the Decadal Committee recommended doing. So I'm going to zoom in on just this narrow area, and Hubble was from 0.1 microns. I convert everything to microns to 1.8, so it goes a little bit into the infrared. Spitzer is further into the far infrared, and Herschel is even farther. The latter two, to cool, needed liquid helium. And when the liquid helium ran out, the telescopes either were completely useless like Herschel, or Spitzer did a little bit of work, but not much. So Webb goes a little bit towards the infrared from Hubble. It can see a little bit of red and orange, but it's mostly infrared. So there are two areas. The near infrared is 0.6 to 5 microns, and the acronym is NIRCam. And every time there's a near in an acronym, that's near infrared. This is a camera, and it's just passively cooled to 40 Kelvin. The mid infrared instrument, MIRI, it needs further cooling to 7 Kelvin, and I'll go into more details about that later. So here's a picture of NIRCam. And I'm not going to go into all the details of the incredibly complicated paths that the light follows, but this is a filter wheel. Sorry. And there's an incredible combination of different filters that can be used. And when someone's making a proposal for an observing run, I'm sure they have to explain exactly what it is. And this gives a wavelength. So F150W would be 1.5 microns, and it would be a wide range of wavelengths. And every time you see a picture, say the 12-hour deep sky one that to me is my favorite, they've used several filter wheels and done a few hours for each. And it's going to be quite exciting when they decide to do 2 weeks, just deep sky, but that's still to come. The sensor, actually, they slightly tweaked the ratio for the two levels in the near infrared. And here's the image that we've all seen of the planetary nebula. And most of the people that paid for the work live in the northern hemisphere. And almost all of the objects are only visible in Michael Watson's favorite hemisphere. Anyway, this is NIRCam. So the blue or longer wavelength is around 1 micron or something or other, or shorter wavelength, I mean. And the longer wavelength, which is red, goes here. And notice it has a significant expansion. This is actually a stretched spherical object. And just like a clear balloon, you can see easily through the straight part. When you get to the edge where you have a thick layer that you're going through, that's what you see here. And I don't know whether these features are on the top, on the front, or the back. I'm sure there'll be research on it. MIRI is a bigger instrument because it also includes spectrographs and other aspects to it, and it's from the longer wavelengths. When you go longer wavelengths, the photons have less energy. And when the energy of the photons starts getting close to the energy of the thermal vibrations, you get huge noise. So what they have to do for MIRI is to cool it even more. So they not only count on the 5 layers of sun shield that are wider at the outside, so any photons inside reflect and go out, but they also have a cryo cooler, and it has to be on the hot side, you know, the sun side of the things. And it has a system where you have sound in a certain way that cools. and it gets the MIRI detectors down to 7 Kelvin. The other telescopes lost their functionality when the liquid helium ran out. Helium and hydrogen are tiny molecules and can easily escape, and I don't know whether they're going to be able to keep this running for much more than 10 years because it's difficult to keep little molecules from escaping. So here's the MIRI image, and I'm going to show both of them for comparison. The NIRCam, the blue is 0.6 and the red is 5. And you get all sorts of details. In MIRI, which is the longer wavelengths, now the blue is the shorter of the wavelengths. So what is red here is blue here. And I have no idea why the center here is blue and the center here is red. Now, I've downloaded the full versions of all the files. And I've taken segments of each of these. So this is the biggest version I could find. And in the NIRCam with the shorter wavelength, you see there's incredible detail here. But in the MIRI, you get less detail. And that's because light tends to bend around objects better when it gets longer, but it also means that the sharpness. And you'll notice that you get the diffraction spikes here in the short wavelength, but relatively few diffraction sites there. And of course, the biggest difference between the two is the star. And here you have 2 stars, and here you have one. Oh, wait a minute. It looks like the second star is on a diffraction grating, but it's so much fainter from the other. The larger, this star would have had a planetary nebula, many millions of years ago. And it's a white dwarf, but the bigger star is 100,000 Kelvin, and it emits mostly in the ultraviolet, and its emissions get less and less as you go further into the infrared. So this is invisible, 250 times brighter than the other star, Mag 10 instead of 16. But when you get into the far infrared, this gets less bright. And the other object gets a little brighter because that's sort of the temperature it is, but I was never able to find the exact temperature. And they get closer in brightness. Now, it also works for planets. If you can take photographs of planets next to stars, the relative brightness of the planets increases, but you also have the reduced resolution by being longer wavelengths, and maybe they'll launch a larger satellite, maybe with 3 Webb telescopes in some sort of structure they build up there. Who knows? But that's an advantage. Now we come to the Carina Nebula. And for many people, this is their favorite image. It's my third choice, actually, if I could rate them. And it's just stunning, the way these colors are laid out. And I don't know if NASA hired an artist to pick out the colors, because we can see none of those. They're all infrared and a tiny bit of red at the one end. It's all invisible, so the colors are arbitrary, but this is a stunning image. Notice the little knob here, and now I'm going to show you this image along with the MIRI image together, but you see the MIRI is smaller, so you lose the knob, and the colors aren't quite as impressive when they come with it. But given that it's the longer wavelength, you can see deeper into the clouds. And the comments said that the really red objects are probably stars that have not yet ignited, but they're forming and getting warm. And I picked an area here because that star was exceptionally red. And I heard people talking about it, and they said that this is probably also a star forming. I don't know. And I wonder if some technician left it cheesy in the equipment. I don't know what that is. Maybe 2 galaxies that are merging in a funny way. I couldn't find exactly where on the Carina Nebula this is. This is my best guess. Maybe Michael knows better than I. Notice that In other instruments, they always make north up, but in Webb, perhaps because it's difficult to adjust, they put north in whatever, they orient it in whatever direction it's the system is working. Hubble versus Webb. Given the more infrared, you can see through the dust better. The Hubble, the dust mostly blocked it, and that's one of the many advantages of infrared, as you can see well into clouds. Pink Floyd. I love this album. It separated me and many others from a significant amount of money. And a prism or a grating where they have a series of lines right next to each other at equal spacings separates white light into its colors, as Newton said. And I teach my students red, orange, yellow, green, blue, indigo, violet. Roy-G-Biv is the acronym, and that's the colors of the rainbow. Now, could I ask Andrew to show me on this image, because there's something I want to show once I finish something. It turns out the visible range of wavelengths is a common energy for electron transitions. And in an atom, you can't have any level of the electron. It's got to be either here or here or here. There are different fixed levels it can be. And you can see that by doing what ancients did. They made sacrifices of fatted calves, and they burned them for the gods, or I'm not quite sure why. But the instructions in the Old Testament book in Leviticus are quite specific. You've got to put lots of salt on them. And when the salt burns and the meat, there's a certain level of the sodium atom that the electron is bounced up. And when it falls back down, it gives off a yellow photon. And that's unique for sodium, the pattern. If you do that with lithium salts, you get red. If you do that with copper, you get blue. And these are all unique patterns to the particular ones. They're spectra. And that's the fourth thing that's unique about there. Infrared is a little different because it's lower energy. And I'm going to pretend, I don't know if you can see my image or not, that I'm doing a chicken dance, and my heart is one atom, and there are two atoms on my elbows. And there's sort of a ground state of a molecule. And then if it gets extra energy, it goes at a higher state, but it can't be any state. But eventually it drops back down to ground state, and it gives off a photon of infrared radiation. At the same time, if you have a atom of infrared, at ground state, a molecule at ground state, and a photon of that energy hits it, it suddenly can go. So the molecules can absorb certain wavelengths, and they also can emit depending on the situation. This all happens at infrared. So infrared is so valuable because we can look at molecule transitions and we can identify molecules. This is a probably 50-year-old graph of the spectrum of the different planets, including Earth, taken from a spacecraft. And Venus and Mars have big dips for carbon dioxide where it absorbs things. But Earth also has ozone. Now, the ozone comes because when you have O2, with two oxygens in the atmosphere, some of them turn into O3, and the O3s turn back, so you get a continual balance. And the presence of ozone in the atmosphere means there's oxygen. And where does oxygen come from? Some people say it has to be green plants, and other scientists are now saying, wait a minute, there might be other ways of doing it, but this would be a biomarker. And there's massive research in biosignature gases, and there are different wavelengths in the infrared that show you've got different biomarker gases. And this paper has a number of references from somebody who used to go to Toronto Centre meetings, and this is Sarah Seeger's core expertise. Now, they showed another star that is too far south for us to see, and this WASP 96 is a sun-like star over 1,000 light years away. I could see it with my telescope if it weren't for the Earth. The planet's a little larger than Jupiter, but not that heavy, and it's one of these hot Jupiters that is it orbits only in 3.5 days. It itself is very hot. Now, when a planet transits a star, it blocks some of the sunlight, and the brightness goes down. And if this is 100%, it might be hard for you to read, but the bottom is somewhere around 98.5, so it drops about 1.5%. If you have an Earth-sized planet, the drop is a lot less. But the planet blocks all the radiation going through it, but the atmosphere blocks the wavelengths of light that are absorbed by the elements, or the compounds, I mean, in the atmosphere. And they released this by NIRIS, which was made by Canada, and unfortunately the Canadian experts weren't able to do. There was some technical issue. You can get to the L2 and everything works, but we can't get communication. And this is the graph they produced. So this is the parts per million are blocked. Remember I said it was, 14,000 roughly. And it turns out certain wavelengths are absorbed more than others. And this shows the presence of water and also sand for some reason, and I'm not sure how they did it. Of course, it's not a surprise that water is there, given hydrogen, I think, is the most abundant element, and I think oxygen is 3, something like that. But this way we can find other compounds that might be biomarkers like O3 or methane or others, and Sarah has citations in this paper as well. I've read, but I can't reconfirm, that something like 1/3 of Webb time is going to be monitoring exoplanets. Now, something the NASA is planning is, if you get a device like this with sunflower-like petals, for some reason it causes the light to bend around it to give particularly sharp images of planets. And if you put it 70,000 kilometers away from the observing telescope, you can see it. I don't know whether they're going to use this with Webb or with another, but you'll actually be able to image and measure spectra of planets, and that's coming. And it could be when at Star Party somebody says, "Do you think we're alone?" Instead of saying, "I don't have a clue," or whatever, we're going to be able to say there are experiments that have found enough biomarkers in other planets on other stars that there's life elsewhere. Exciting. Stephan's Quintet. This was taken on a lousy night by a friend of mine, and Hubble took a slightly better version. And there are 5 galaxies that Stephan identified as a group, but the northeast one is 39 million light years away, which is 15 times the distance to Andromeda, and the others are something like 120 times the Andromeda distance away. They get this from the speed, and I'll talk more about Doppler shift later on, but it turns out the whole universe is expanding. That's comes from the Big Bang, and objects that are this sort of distance away are moving faster. And it turns out when you divide the speed by the distance in megaparsecs, you get the Hubble constant. So this divided by that is somewhere around 70, 71. Here's the Webb versions. Notice the NIRCam, they're relatively smooth, but the MIRI picks up all sorts of details. I don't know if these are star-forming regions in here. This upper galaxy with a very active core. Notice the incredible detail that comes out. I have no idea what they are. The Miri has a smaller space, and they just didn't get the elliptical galaxy down there. That's relatively uninteresting. This is the combined version of the two of them, and I'm just going to zoom in on a couple. Sorry, I'm going to zoom in on a couple. This here shows the part of the galaxy, the nearby galaxy. You can actually see what seem like stars and star-forming regions. And this shows various things of this galaxy that seems to be merging or whatever with the other galaxy. And somebody said you can see an image of the jets that come out, but I can't see anything here, but that's another story. Oh, sorry, I went too far. But there are all sorts of things in this image that might also be of interest, like distance objects. And what they want to do is to be able to get a spectra of a lot. And it's a little bit like the Digital Sloan Sky Survey. It's New Mexico, and they want to take a whole bunch of spectra. So what they do is they get an aluminum sheet that goes right at the focal plane of the camera. And then what they do is drill holes where they know galaxies are going to be, and they stick fiber optics in each of the holes, and then they take a long exposure of that area, and they get a whole bunch of spectra, and that allows future scientists, other astronomers, to say, oh, this has interesting characteristics, let's do further study, and it's made some interesting discoveries. I asked Jim Hesser about this because I didn't know the name of it, and he gave it to me and also said that at the DAO in Victoria, some astronomers tried to make a device with doors that would open at the galaxies, and Webb has perfected it, and they have a whole bunch of micro shutters that can be opened for something. Unfortunately, some of them are jammed shut, and a few of them are jammed open, which will contaminate nearby things, but that can all be worked around. And here's a field, I'm not sure from which picture, but they have picked a particular thing. So this is like almost 2 arc seconds, and they take the specific spectra of that area and they get individual spectra. They also have something where they break the whole image into pieces with this device, and then they take many spectra at once. Anyway, here's where they took the spectra around the active black hole in the upper galaxy, and this is too hard to see, so I'm zooming in. And I also drew the diagonals, and you can see that this part of the galaxy is moving towards, and this part is moving away with the different ions, and they get this from Doppler shift. And they can find the composition around there. But my favorite image is this one. And this is what Joe and Kamala got to see, along with NASA brass, who obviously want to get more funding. And you've all seen the deep image. I had trouble. I can't find the exact size of the image. And my guess is from a grain of sand at arm's length that it's probably, this is an arc minute. And it turns out they have this galaxy, and it bends light from elsewhere, and you get these Einstein rings. So there's an Einstein ring. There's an Einstein ring. There are 3 Einstein rings in a row here, and maybe others. And what happens is you have a heavy mass and a distant object, and the mass, if it's lined up with where you are, you can get these rings that don't always have the same radius or whatever. It very much depends on it. And sometimes you get a ring that actually magnifies something. And here they found a star that didn't appear in 2011, presumably from Hubble. Yes, it is. And in 2016 it appears, and it could be that it just happened to move enough in the 5 years that it now got magnified by 2,000 times. And my first thought was, well, maybe it's a supernova, but apparently it's kept the same temperature all the time. So it's the same star, and it's 9 billion light years away. That's like 2/3 back to the Big Bang. Who knows what Webb might find? You also have sometimes you get 4 images of the same quasar or object in a row, and these give information on distant objects magnified, but also they can do statistical studies and find foreground masses, and that will help learn about dark energy or dark matter. Now, details, I downloaded the big version that I don't know is 100 meg, something like that. And I decided to pick my 3 Einstein rings. And what I did is I moved the image down, and you've got it to the top. So this is showing the 3 Einstein rings, except, oops, this looks like an Einstein ring, and it's got a little bend to it, maybe the central object. But this to me looks like a galaxy. And I don't know what this is. I don't know if those are globular clusters. I don't know. I presume it'll come up. And here's a comparison of NIRCam plus MIRI. I couldn't find NIRCam alone, and MIRI only. And it looks like MIRI is a fuzzier image, not showing details. Remember, I said the longer wavelength has less resolution. But the other thing is, I think MIRI, maybe they didn't take as long an exposure because it doesn't show as many things, but maybe it would never show that because the resolution isn't good enough and it's just fuzzy. Who knows? And I just let you look at fully resolved area to what I thought was 3 Einstein rings. Beautiful. The deep image was taken over 12 hours, and my guess is it's a few hours with one filter and a few hours with another. And who knows what Webb is going to discover when they decide to take 2 weeks and just look at the same patch of sky like Hubble did with his deep fields. I talked about the different distances to the Stefan's quintet and the speed. And the speed tells us how far away things are. And I'm getting close to the end by showing you this image of this field, and they picked certain places to take detailed spectra for. And this is too small to see, so I'm going to show you this part in a sec. So you're going to see this in a sec. But I'm going to start with spectrum lines from rest, i.e. the measuring. This is in a lab in Earth, so there's no speed between them. So you have your hydrogen alpha, and it's somewhere around 6.5 to 7, 0.6 to 0.65, something like that. You have your oxygen 3, and Eric talked about is hydrogen beta filter, and you have a line here, and this is what you have at rest. Now, here's that part for the top one, and it looks like because the galaxy is, we're moving away from the galaxy, or the galaxy's moving away from us. Einstein says relative motion is the only thing that counts. And what you've got here is what the O3 line was 0.5 micron is now almost 2. So the red shift is almost 4. Now, let's look at some of the other ones. This one is 12.6 billion light years away. And the one that was 0.5 is now over 3. So the red shift is like 6. And here it's 4 and a bit. So the red shift is maybe 9. And this one that's 13.1 billion billion years is closer to 10. Who knows what they're going to find when they do the deep field. So what I did is I zoomed in using the large scale on this image, and here's the galaxy, there is there, and the 2 stars, and I think that is the image of a galaxy 13.1 billion years ago, and that's about 600 million years before the Big Bang. The early universe was very dense because all the mass was concentrated. And they figured there were population 3 stars with just hydrogen, helium, a tiny bit of lithium and beryllium, and no metals. And these are the heavier elements in order in the sun. Because they lacked these elements, huge stars would have formed, and they would have had a short life, and the supernovae would have made metals for future stars. By metals, I mean elements like this. So this is part of how the early universe started. And seeing back in the cosmos, the Hubble can go to about 1 billion years after the Big Bang. Webb so far has gone something like 600 million years after the Big Bang. Maybe they'll be able to go further. I've heard different stories, but nothing that I've confirmed, so I haven't mentioned it. And that will be exciting. So what is we getting out of the Hubble? We're going to, or the Webb, we're going to learn about how stars die and recycle, how stars form, because in infrared you can see through the dust, how galaxies interact, the early history of the universe, and maybe we're going to find the answer to that age-old question, are we alone? Thank you very much.
Thank you very much, Ron, for a very timely presentation, and also for doing all of the research and sharing it with us. Great presentation, Ron. Let's go to questions. Emma, do we have any questions for Ron?
Yes, we have a question. TS asks, why do Einstein rings happen?
Einstein's theory of relativity, general relativity, predicted that the heavy bodies deflect light rays. And in the 1919 eclipse, somebody took a picture of a star next to the sun during an eclipse, and he was able to show the star appeared further away from the sun than it should because the sun had bent the rays. So if you get a big galaxy between us and something more distant, what happens is the galaxy deflects the rays and they come towards us. And sometimes you end up with 4 images like an Einstein cross. And sometimes you get these curves like right there. And a study showed, by the way, that this curve is the same redshift as that one. So it's the same galaxy. I wish I could go further than that to explain it, but it's deflection from something more distant. Okay.
Great. Thanks. Eric Briggs had a comment for you who said, MIRI's cryocooler is a closed system, so it isn't designed to eventually exhaust its coolant, which is new tech.
I completely agree, but it's very difficult to keep helium in something. And I read somewhere that there's worry that in 10 years they might lose some. I agree in theory it's done, but helium's a small molecule and it tends to wheedle out. Anyway, but I agree, Eric, it's supposed to be contained.
You also got a question from TS as well, who asks, how short-lived were those stars?
I'm sorry, which stars is... the population 3 stars?
Yeah.
Nobody's found a population 3 star yet, although there might, maybe yes, maybe no, so they don't really know, but I think they expect them to last just a few million years and then go boom, because they're like 100 times the mass of the sun, because they don't have, especially carbon monoxide. The problem is you have a layer of gas and dust, but it's all moving and it can't squeeze closer because the there's the thermal motion of all these things, so it can't get there. So by having carbon monoxide present, it gives off infrared radiation that leaves. It can cool and get bigger, and eventually gravity forces it into one. That's a population 1 star like our sun. The population 3 stars don't have any of that, So they have to get massive before the gravity's enough to pull them together. And I've read that just a few million years and then they go boom.
Cool. You got a few comments from CDB45 who says, interesting presentation, thank you. Serge Roy also says, excellent presentation. And Zapfan says, looking into the period of reionization. And Sue also says, thank you for your outstanding research.
Okay.
And that's all the questions and comments we got tonight.
Thank you. And there's talk here, I guess I didn't show reionization. And I wish I knew more about cosmology to explain it. You notice I was kind of waving my hands at that stage of the talk because I'm not there. Well, thank you very much. It's really exciting to watch what Hubble's producing. I just want to show one cartoon where the wife is saying the James Webb Space Telescope is showing us images from 13 billion light years away, practically beginning of the universe. Doesn't it make you ponder the miracle of our existence? And her husband says, we're out of beer. Anyway, who knows what's going to happen. So thanks very much, everybody. Bye-bye.
Thank you very much, Ron, again.